Hello everybody! In this clip we introduce intrinsic quadrics, we see a recipe to construct all of them, and we survey some results. An intrinsic quadric is a projective variety with a Cox ring defined by a single purely quadratic relation in such a way that the variables define homogeneous elements in the Cox ring. Similar to the toric varieties, the intrinsic quadrics form an easily accessible example class of algebraic varieties. Let us estimate what we gain by this example class. A normal projective variety with finitely generated divisor class group is a toric variety if and only if its Cox ring is a polynomial ring. So, morally speaking, the ratio of toric varieties by arbitrary varieties with finitely generated Cox ring is reflected by the ratio of graded polynomial rings by factorially graded affine algebras. Passing from the polynomial ring to an algebra defined by a single quadratic relation is a quite controlled step in this context. In that sense, the intrinsic quadrics provide a cautious extension of the example field given by the toric varieties. Let us look at an example. Consider the factor algebra of the polynomial ring in 4 variables by the ideal generated by the quadratic polynomial t1, t2 plus t3 square plus t4 square. Then R gets graded by k equal z plus z mod 4z by defining the degree of the ith variable to be the ith column of the matrix Q. Observe that for the two squares, the degrees of the corresponding variables are distinct. This grading turns out to be factorial. Even more, with the canonical generator system and W equal 1, 0, we obtain a Bunch ring and thus a variety, which by definition is an intrinsic quadric. It is interesting to take a look at the generator matrix of the fan of the minimal ambient toric variety of X. If we arrange it correctly, then in its upper rows it stores the exponents of our defining relation. We come to our systematic construction of intrinsic quadrics. It begins with a quadratic polynomial GQT having terms t1, t2 up to tq minus 1 tq and further squares tq plus 1 square up to tq plus t square. GQT lives in the polynomial ring in variables ti and sj, where the variables ti are precisely those showing up in GQT. The aim is to install a grading on the factor algebra. In the first step, we store the exponent vectors of GQT in a matrix P0. In the first column, we have minus the first exponent vector, and the remaining ones are put into the diagonal, and all other entries are 0. In a second step, we enlarge our matrix P0 to a matrix P having pairwise distinct primitive columns that generate the column space as a cone. The upper part is given by P0 in the 0 block. The lower part is given by blocks D and D prime, which can be freely chosen subject to these conditions. In step 3, we define the gradient group K to be Z to the n plus m modulo the image of the transpose of P. Then we see projection from Z to the n plus m onto K. We obtain a K-graded factor algebra R of P, where the degrees of the variables are the images of the corresponding canonical basis vectors under Q. We call R of P a standard K-graded quadratic algebra if the degrees of the variables that show up in the squares are pairwise distinct. The K-grading of R of P turns out to be almost free and factorial. Moreover, R of P is a unique factorization domain. If and only if we have at least 5 variables showing up in the quadratic relation. Now, given a standard K-graded quadratic algebra, we want to gain intrinsic quadrics out of it. We obtain a Bunch ring, RFW, by taking F to be the canonical system of generators and choosing W from the relative interior of the moving cone. That means W is contained in the relative interior of any projected facet of the orthogonal gamma. Now we go with our Bunch ring into our usual construction. This gives us a variety X, which has R of P as its Cox ring. We call X a standard intrinsic quadric. Note that in the particular situation, our total coordinate space is the zero set of the defining quadratic polynomial. Moreover, X hat is the set of semi-stable points of W. The matrix P is a generator matrix for the felt sigma of the minimal ambient toric variety of X. As a matter of fact, any intrinsic quadric is isomorphic to a standard intrinsic quadric. Finally, we take a look at known statements about smooth intrinsic quadrics of low Picard number. First, in case of Picard number 1, there is only one type of examples, namely the classical smooth projective quadric in at least 5 variables. Here's an example of Picard number 2. Look at the quadratic polynomial with terms t1, t2 up to tn minus 1, tn, where n is at least 6. Then we obtain a Z2 grading on the factor algebra by assigning to the odd variables degree 1, 0 and to the even variables degree 0, 1. Now if we take W equal 1, 1, then we obtain the Bunch ring, and the associated variety is an intrinsic quadric. It is the flag variety of type 1, n over 2 minus 2, 1. And the minimal ambient toric variety is an open subset of a product of projective spaces. We speak of a full intrinsic quadric if all variables show up in the defining relation. The full smooth intrinsic quadrics of Picard number 2 turn out to be the flag varieties we have just seen. In Picard number 3, it is still possible to give explicit descriptions in that spirit of all full smooth intrinsic quadrics. If you look at full Fano intrinsic quadrics, smooth or not, then the Picard number is bounded by 3, and in Picard number 3 there are no smooth examples. In fact, all Fano full smooth intrinsic quadrics are given by these varieties on the right hand side. If we leave the full case, then it's still possible to give explicit descriptions for all smooth intrinsic quadrics of Picard number 2. See you in the next unit.